So the first clustering method we're going to look at is called K-means clustering. It's a very popular method and it's very simple and very easy to implement and use. So we're going to be in a situation where we imagine we've got n data points again, x1 up to xn, and our goal is going to be to allocate each of the observations xi to one of k clusters, which I'm going to call here C1, C2 up to CK, so that are k clusters. Remember that these might not be physically meaningful things. So we've looked at data where there are meaningful clusters like iris species or digits, but that's not the case here. We're going to try and find the clusters ourselves, so the clusters may or may not be meaningful after we're done. So we're initially going to assume k is known to begin with, but we'll look in a moment at what happens when k is unknown and how to estimate k. And we're going to want to find clusters so that points within a cluster are more similar to each other than they are to points in other clusters. So we're going to assume that the clusters partition the n cases. So in other words, if we look, we're going to assume that each xi is in some cluster Cj. Okay. And we're going to assume that if we look at the union of all the clusters, so that's j equals 1 up to k, we're going to get all the points back again. Yeah, so each point is in one cluster. We're also going to assume that the intersection of any two clusters is empty. So for j not equal to j prime. Okay. So each point is in precisely one cluster. So if we have a quick picture, if we imagine in 2 dimensions a bunch of points, okay. So it looks like there's 2 clusters here, and what we're going to do in cluster analysis is assign each point to one cluster. So maybe we make this cluster 1, and maybe we make this cluster 2. Or maybe we do it some other way. Yep. But this is a clustering that makes the points within a cluster look more similar to each other in some way. We're going to define what we're going to call an encoder. So this is a function delta I, we can think of it as, or we might think of the vector delta 1, delta n. Oops, sorry. And the encoder tells us which cluster observation I is in. Okay, so we have that delta I equals j if and only if xi is in cluster j. Okay. So delta just tells us which cluster each observation's in. So if we had point 1, point 2, point 3, point 4, etc. here, we would have that delta 1 equals 1, delta 2 equals 1 because it's in cluster 1, delta 3, well point 3 is in cluster 2, point 4 is in cluster 2, etc. Okay. The delta just tells us which cluster each point is in. So we can think of delta as a vector of n integers, okay, where delta I takes the value 1 up to k if we've got k clusters. So we want to estimate delta some way. So remember, our aim is to find delta so that points within a cluster are more similar to each other than points in other clusters, So how can we do this? Well, we could use the loss function that we saw previously. So we saw already what we called the within cluster. Well, we had variance before, didn't we? But let's call it spread here. The within cluster spread. So that we can sum over the different clusters. Okay, so let's make that lowercase k. So sum over the different clusters, and then for each cluster, we could look at the spread of points within that cluster. So let's have the sum over I such that delta I equals k, and the sum over I prime such that delta I prime equals k. So they're lowercase k's, aren't they? So let's try and make that clear. And then for each, we could just sum up the distances between xi and xi prime. So this is adding up the sum of the distances within a cluster. Yeah, so for cluster 1, we look at all possible pairs of points and look at the distance between them and add them all up. We do the same for cluster 2, same for cluster 3, and so on. Oops, I missed a factor of 1/2 here. Yeah, half because otherwise we add up these distances twice. Yeah, so we add them all up twice here, so I just divide by 2 to get the total sum of distances. As we saw in the previous chapter, we can split the total spread into a within cluster spread plus a between cluster spread. So let's write that out. What's the total cluster spread? Well, the total cluster spread is just a sum over I prime. Half of it, and dxi prime. Yeah, it's just the sum of all the distances between any two pairs of points. Well, let's split this up. So we can split this up into the sum over the different clusters, k equals 1 up to k. Remember, each point is in one cluster. Well, then let's have all those i's such that delta I equals k. And then we can add this in, split this into an I prime such that delta I equals k, the d xi prime plus the sum of I prime such that delta I prime does not equal k, d xi prime. Okay, now this first term here is our within cluster spread, and the second term here is going to give us the between cluster spread. So we can see that minimizing the within cluster spread is equivalent to maximizing the between cluster spread. Yeah, because the total spread doesn't change, t doesn't change, there's no delta over here on this side. Okay, so delta only appears on the right hand side here. So we can either choose to maximize w, minimize w, or maximize b. So the type of optimization problem we take, the way k-means works, is to try and find delta to minimize w of delta, the within cluster spread. Now, unfortunately, when we think about how to do this, how many different ways there are to allocate observations to clusters, it's going to explode combinatorially. As n gets even moderate, and as the number of clusters grows small, so even with 100 data points and 10 clusters, that is far too many combinations to search through them all to evaluate w for each possible allocation for each possible encoder. So instead, we tend to take a kind of a greedy iterative approach. Okay. So let's just say we can't solve this optimization problem generally. So we take a greedy iterative approach. Okay, so the idea is we pick an initial allocation and then at each step change delta to decrease W of delta. So just note this can result in finding local minima. Yeah, so we might find a local minimum point rather than the global minimum point. So what we tend to do is to run the algorithm multiple times. So we pick many different initial assignments, delta, and we use this greedy iterative approach, and then we compare all the answers we get at the end. So far we've not specified the distance function. The k-means uses the distance function d xi and xi prime is the squared Euclidean distance. Now, what we said so far, we can use different distances. You can use the median, you can use all kinds of different things that have been proposed here. But if we use the squared Euclidean distance, in that case we get a nice simplification. We find that the within scatter cluster reduces to being sum of k from 1 up to k. Nk, okay, where nk is the number of points assigned to cluster k, so that's the sum of delta I equals k, indicator delta I equals k, I equals 1 to n. Okay, so it's the number of points assigned to cluster k. Okay, so we get this is sum nk sum I such that delta I equals k, and we get xi minus mu hat k squared. Okay, where mu hat k is just the mean of all the points in that cluster, so it's 1 over nk sum of the xi's, where we're summing over I such that point I is in cluster k. So this is the mean of points in cluster k, and you'll note this is related to the variance of points in ck. Yeah, it looks like the sum of the within cluster variances are proportional to. So you'll be asked to prove this on the example sheets. So the algorithm used then is as follows. So first of all, for a given assignment, cluster assignment, for a given encoder, we find the cluster means mu hat 1 up to mu hat k. And the next step is, given the cluster means mu hat 1 up to mu hat k, we're going to assign each point xi to the closest cluster mean. Yep, so in other words, we're going to set delta I equal to the value that minimizes, the value of k that minimizes the distance between xi and the current cluster means. Okay, and then all we're going to do, we're going to iterate steps 1 and 2 until convergence. So think about this. We start with a cluster assignment delta, we find the mean of each cluster. Then given the means of each cluster, we assign each point to a cluster according to which mean it's closest to. Then with that new cluster assignment, we reevaluate the means, then we reevaluate the clusters, reevaluate the means, reevaluate the clusters. And you can show that this will decrease the within cluster spread each time. W decreases at each step here. And eventually it will converge and settle down. Okay. But as we said, it might converge to a suboptimal local minima. So we tend to run this algorithm several times.